Hello guys, welcome back to Magnetic Effects of Current. In our last class, we did two important formulas based on Biot-Savart's law application. What was those? Number one, we found out a magnetic field due to straight current carrying conductor for infinite length. That was a special case. What was the magnetic field formula? B was equal to mu naught I upon 2R, right? This was for full magnetic field. This was the special case for infinite length from both the ends. Another was, it was a semi-infinite when you have the wire and your point of observation is at one of the end. So this will be taken as semi-infinite. The formula was mu naught I upon 4R. Are these two formulas right? Sure? There is something wrong in this formula. I have not written this word pi. Remember this. Circle, magnetic field at the center of the circle B is equal to mu naught I upon 2R. Now this word pi, this is how I have memorized it. This word pi is 2R. This word pi, alphabet pi or symbol pi is associated in a lot of ways from the circle, right? Like circumference, area, etc. So this pi is not in the formula. This is how I have remembered the answer for magnetic field at the center, which is equal to mu naught I upon 2R. For this, for infinite length, it is mu naught I upon 2 pi r, and for semi-infinite, it is mu naught I upon 4 pi r. What was the basic formula for any generalized formula for any semiconductor? It's not semiconductor, any conductor having current I and distance r. General formula was, if this is my point of observation, which is at perpendicular distance r from this conductor carrying current I, so in that case magnetic field would be mu naught I upon 4 pi r sine theta 1 plus or sine phi 1 plus sine phi 2, sine theta 1 plus sine theta 2, sine phi 1 plus phi 2, whatever. Where is phi 1? This is our phi 1 and this is our phi 2. Sorted? These are the few formulas. Let's do a quick application of these formulas with some examples. Okay, take the first example. I'll show you a diagram in which you will tell me the magnitude of magnetic field along with the direction. What was the rule associated with the direction of magnetic field? That was right hand thumb rule, right? So okay, I can in brief again tell you what is right hand thumb rule. This is your current carrying conductor having current flowing in this direction. So place the right hand of your place the thumb of your right hand in this direction, the direction of flow of current. Then curling of fingers gives you the direction of magnetic field. Like magnetic fields are like this, like concentric circles. Now I'm giving you three examples, out of which you have to solve all three obviously. Number one is, this is how current is flowing. This is radius r and this is semicircular part, current I. This is one of the diagram. Second diagram is, current is coming in this conductor, undergoes a circular path, which is very weird circle. So I will redraw it. Now it is a bit more like circle. And in the third case, the third diagram states, current is coming like this, circle is completed like this. So this is how current is flowing. I want you to give me the magnetic field at point P in all the cases. Alright. See what will be the change in method when we are solving for these three. First of all, whenever you get any question from magnetic field of current, always go for the direction first direction and then the magnitude. How do you find the direction? For one of the rule is my inverse right hand thumb rule, which states fingers in the direction of current and thumb will give you the direction of magnetic field. So ultimately magnetic field is vertically outwards, right? Otherwise, for this part, this when your ends are not given in the diagram, you will consider it as what? It will be an infinite or semi-infinite case. So magnetic field due to this wire will be considered to be B1. For this semicircular wire I am considering B2, and for this conductor I am considering B3. I should not be writing B2, B3 here because I don't want you guys to get confused. I just want you to know that I am writing this B1 for this conductor, B2 for the semicircular, and the third B3 is for straight wire. So let's see the directions first. At P point, magnetic field due to first conductor part, this much part, will be vertically outwards, thumb in the direction of current, fingers vertically outwards. For the semicircular path, current is going like this, right? So again this is vertically outwards, and for this part again this is vertically outwards. So for all the three cases direction is same, so ultimately net magnetic field would be what? Sum of individual magnetic fields, and that is B1 is due to straight current carrying conductor of semi-infinite length, that is 4 pi r. Then B2 semicircle, what is semicircle? Mu naught I upon 2r is circle, that means 4r is for semicircle. And lastly mu naught I upon what? For this also 4 pi r, right, for the straight. After this, don't have to solve it, right, completely in such kind of questions. You have to take all those common things which you can take out. Here I can take out mu naught I upon 4r is common everywhere, so 4 into r. I am left with 1 upon pi plus 1 upon pi. So this gives me 2 upon pi plus 1, right? So this is my final answer, mu naught I upon 4r 1 plus 2 upon pi. This is my final answer. This is the magnetic field. And if you want to represent the direction as well, so right here, now I am representing it in vector form. So what will be the quantity I will be adding here to make this whole thing in vector? I will be adding the direction, and direction will be, it will be I cap, right? No, because magnetic field is like this, vertically outward. So what is this? If this is your y plane, x plane, and vertically outward z plane, so this what was vertically outward, that was z plane. So k cap, sorry, I should have used this, so k cap. So this completes your value, the magnetic field. Similarly for this, magnetic field at center for this part would be vertically outwards, for this part also vertically outwards, and for this circle it is not like this, it is like this, right? Current is flowing like this, so magnetic field vertically inwards. So now you definitely have to subtract one of these. If magnetic field at P point due to this much part is B1, due to this hole is B2, and due to this part is B3, definitely these two are going to be B3. These two are going to be added up because they are in same direction. B2 is going to be subtracted, right? But which, B2 minus B1 plus B3 or B1 plus B3 minus B2? This can be obtained only when we know which is greater, which is less. So we can just write down, first find out B1 plus B3 is what? B1 plus B3 is mu naught I upon 4 pi r plus, which is this semi-infinite and this semi-infinite, mu naught I upon 4 pi r, right? So 2 mu naught I upon 4 pi r, 2 gets cancelled out, mu naught I upon 2 pi r, which is equivalent to the magnetic field at a point due to like straight infinite length. So two semi-infinites make one infinite, even if it is there is a small gap in between, it doesn't matter, right? It is negligible. So this is the final outcome, B1 plus B1 plus B3, not B2. I did this mistake like twice or thrice in this whole page, right? Anyhow, for B2 is mu naught I upon 2r, because it is a complete circle, a small gap doesn't matter. So for complete circle it is 2r. So which one is greater, this one or this one? Denominator is higher this side, so that makes this whole term smaller. B2 is greater. So net magnetic field would be B2 minus B1 plus B3. Sorted? So So net magnetic field would be this mu naught I upon 2r minus mu naught I upon 2 pi r, out of which I can take out this thing common, so I'll be left with 1 minus 1 upon pi. This is my final answer, B. And if I have to write it in vector form, this form, like with the direction, and net magnetic field is due to the bigger part. Bigger part is the direction of magnetic field due to bigger is minus k. So I would write k cap with a negative sign here. This completes my answer. And now similarly you guys have to find out, it will be this, the answer of this and this will be exactly similar with just a small difference. What is that? Magnetic field due to this straight part will be vertically outwards k cap, for this vertically outwards k cap, for this vertically outwards k cap. So you will be actually adding up B1, B3 and B2 and you will get plus here and plus here with the same answer.